All right, so let's get started. My name is Jan Monsch. I'm a security engineer in the Google security team, and I work in a group which is responsible for protecting the corporate infrastructure of Google. And we have been doing some research how we can actually validate the firmware running in our corporate fleet, which is actually very diverse. So we have everything you can almost think of. And over the course of this research, we figured out that it's actually really hard to verify all the firmware blobs which are inside the machines we have. So looking, stepping a little bit back and figuring out what do we really need to do. And I realized that we actually need to have improvements in the industry, like the people who actually work on firmware, work on the hardware parts, to get to a point where we can actually verify the firmware on these devices. And also that we can improve the security of the firmware in the devices. All right, so in my talk here, I'm going to propose a few things of how I think that we could improve the firmware security in the industry. And I'm very much happy to hear your feedback and maybe new ideas in addition to what I'm talking here about. All right, so what is the agenda of this talk? So first, I want to talk about the motivation. So why are we doing this at all? Then I want to talk about the challenges of actually verifying firmware in practice. And last but not least, the proposal of how I think we can improve industry practices. So why do we care? Well, first of all, what is happening in the wild? So we have some knowledge of state-sponsored attackers actually using firmware implants. And there are a few examples here, like the Equation Group, which is a group doing ATP type attacks. They've been, we can see in the hooks they have in their operating system side malware that they actually have a hard disk implant. But we also know from the Snowden papers that there are firmware-based attacks happening. Like IRID-Monk, for example, is a hard disk firmware attack, which basically replaces the master book record on booting of the device, and that's how they get actually control of the machine. There's also another type of attack, data bounce. Basically, the idea is that attackers are able to install malicious firmware either remotely or by interception of the device in the supply chain and flash it with their own firmware, and basically also getting control over the device this way. There are also a few other projects, but I'm not going to iterate over all of them. Now, something which came up last year is that we actually saw that non-state-sponsored attackers are picking up this technique. And probably the first one of them out there is the hacking team, which modified UEFI firmware for a particular platform to drop malware payload into the operating system through a modified UEFI BIOS. And it actually persisted. So you can remove the operating system, reinstall it, and it will put back the malware on the OS. All right, so why is this attractive to attackers? Well, first of all, the investment to actually do this type of implants is actually very high. It requires specialist knowledge of hardware, firmware. They need to do a lot of reverse engineering to figure out how these components actually work, to figure out where can they put in their implant. But also they need to make sure that it's reliable. Whatever they produce needs to be reliable enough that the user doesn't notice that something is wrong with their device. However, it lasts for a long time, and this is in particular due to a very low chance of detection. Like the standard tools that people use to manage their platforms actually doesn't check the firmware bits. Is the original firmware still there? Who knows? So that means for an attacker, it's very, they have a high investment, they get really long-term gain for it. Another thing is like it's still very easy to modify certain firmware on components because there's a lack of protection. Like we see in some systems who don't protect like the BIOS properly, and that means that if somebody gets like root privileges on a machine, they're able to like reinstall the BIOS with something of their own choosing. And the other part is like interdiction, like the supply chain where stuff gets shipped around is not very secure. Like we have seen cases where hardware was shipped from A to B within Europe, and it turned out, or it showed up according to like the traces we see with the shipping companies in places in the Far East. So we actually have no guarantee that the supply chain actually does the shipment the way we think it would go. All right, so what do defenders want? So what do we want? So first of all, we want to increase the cost for actually performing these types of firmware attacks. And that goes by actually removing like trivial security flaws. So a typical flaw could be that, for example, update functionality for firmware is not secure enough. The firmware is not validated when it's loaded, or for example, there are like bypasses which easily allow you to like disable checks inside like the update functionality. As defenders, we also want to increase the chance of detecting these implants in the wild. And overall, we want to like reduce the time that an attacker can expect that these implants will actually work for them before they are being detected. And last but not least, like we want to actually make sure that we are protecting our users and our data. Okay, so let's move on. So let's formulate like a problem statement. So under the premises, we actually trust the vendor of components and devices. So how can we actually verify that our hardware is running vendor-provided firmware? Okay, so most people actually think of firmware in terms of UEFI or coreboot firmware. And it's usually the one which is like the easiest accessible for a verification. So it's stored in SPI flash, and there are tools like ChipSec where you can actually dump the SPI flash and you can see what's inside and verify it. However, there's some caveat with it, like depending on how you read the SPI flash, you might actually see some parts or not. So if you do like hardware-based read of the SPI flash, you see everything. So basically you attach a probe and you can read the whole content. But if you read through like the software part, so let's say through ChipSec, you will only be able to read like the BIOS part, but not the management engine part, because the management engine part is protected in the flash descriptor. With permissions, so only the management engine can read its own code. So that kind of makes it hard to verify. So, but apart from the BIOS firmware, there's a lot of other firmware in a computer. So when you look at the machine today, to me, it resembles more like a network of microcontrollers. It's a whole bunch of these days. Like you can expect that there are anywhere between 10 and 50 microcontrollers with firmware running in a typical laptop. And all of these components have different privileges. So some of these components interact like with very high privilege buses, like they can actually DMA via PCI Express. Like think of like a Wi-Fi card, which has PCI Express connectivity, but also like the GPU has direct memory access, can snoop on the memory. All right, so let's look at an example where you can find firmware running. So this is like a shot of the Pixel 2. And I'm just going to quickly run through where you can like find firmware stuff. So first off, like the CPU, we already heard in a previous talk, like microcode. I would consider it as a part of firmware inside the CPU. We have the BIOS, we have the management engine code. We have like the graphic card firmware. Then the embedded controller to deal with like bring up of the application processor and handling keyboard reading, etc. We have an embedded controller for power delivery, which actually talks to like the power supply. So the power supply in a Pixel 2, I mean like the VART or the block you have outside and you plug into the mains also runs firmware, and the EC power delivery controller actually talks to the power adapter to negotiate the power. And another interesting note is that the Chromebook is actually able to update the firmware on the power adapter. Then the TPM is also a type of microcontroller which runs firmware inside. We have like the SSD drive, same thing, has firmware to implement the SATA command handling, but also deal with the management of the NAND flash memory cells and maintaining it and refreshing things. We have the Wi-Fi adapter, there's firmware. The camera has firmware. There's the touch screen in a Pixel, has also firmware. Touchpad, battery fuel gauge. Yeah, that's where you can firmware running in all kinds of forms. And I'm probably like I forgot a few. Like I'm pretty sure I haven't. I didn't hear you. Yeah, and what did you say? Yeah, so you see, like we are already like probably over the 15 mark at this point. Okay, so you see, there's like a bunch of firmware, and like verifying all these things is actually not that trivial. So verification process, like how does this work? Like usually you would take a component and you figure out a read primitive to actually read the firmware from it. And then hopefully you have like some reference you can download from the vendor to actually do a comparison. Either the reference is a firmware image itself, but it could also be a set of hashes. So sounds simple. Well, actually, as I pointed out, it's not that simple. So let's look why this is challenging. So first, want to make a little digression into like the quality of read primitives. So here's a table of a set of read primitives, and there are probably more read primitives or types of read primitives than in this table. So when you look at read primitives from a security point of view, you want to make sure that you get like the highest trusted read from a component, because then you can be sure nobody like is able to like modify the read what you're doing. So reading through the hardware interfaces itself would be ideal. So think of the SPI flash, and you attach like a probe and directly read the SPI flash. That's how you can get like a high trusted read. But on the other hand, it's very hard to scale. Like if you want to actually scale the analysis across a fleet of a couple of 10,000 machines, this is not a viable approach. Also, some of the read primitives require more specific gear and equipment. So probably like reading the SPI flash with a probe is probably the easiest. But if you want to dump via JTAG, you need to have like JTAG probes, and you have the right JTAG tooling like OpenOCD to actually do the dump. Then another type of read is actually through the firmware itself. So you can think of, you have a component and it runs persistent firmware, and it actually exposes an API that you can read the firmware. But the problem is the persistent firmware might actually like intercept what you're reading and give you back false data. There's also the challenge that some of these components might actually be not connected directly, or like the read primitive is not connected to like the application processor in a way. So there might actually be UART pins which expose a console which might contain read and write primitives in there, but they're actually not hooked up. So you can't use this. But in general, like this approach is like high scalable. Like you can scale it across the whole fleet, but you have the caveat that somebody might actually fake the responses. Then a middle ground way of read primitive would be, for example, to use the OTP firmware. So some of the microcontrollers actually have little bootstraps to install the firmware inside of it. So, and that usually works by, for example, pulling certain pins on certain levels. And then like the boot firmware starts and you're actually able to interact with it and get a read of like the flash portion which contains the persistent firmware. All right, so what other challenges do we have with the read primitive? So a major concern is that it's actually hard to know where all the firmware is where all the firmware is located. It's not like the 1970s where you have a little folder on the back of your TV with all the schematics and you see all the components, what is going on. Today, like you hardly find the schematics and what is used. So it's not clear what devices are built into the laptop and which one are using firmware. And also the data sheets, like if you're able to actually decode the chip label and look it up on the internet, you might find only like a product sheet and you actually don't see the actual interfacing for read primitives. Like especially more specialized components today only have like product data sheets online, and you need to have like a contract with the vendor to give you like the official data sheet if you want, with all the technical details. And in some cases, like apart from not being well documented, like the read primitives are not well documented, they might not even be implemented. Just think about like let's say a hard drive with a SATA connector. There's actually a download microcode instructions, but there's actually, that means like download to the device, but there's actually no function to actually read it. Okay, so that's the challenge with the read primitive. On the other side, we also have challenges with actually doing the comparisons. So ideally, you go to the vendor's website and you had the firmware there to download, and you can then build your tool to compare it. But often, only the newest firmware update is available for download. And but in reality, when you look at the devices, often firmware is not super well managed, so you have all kinds of versions. Maybe you have a revision A of a device with the version 1 of a firmware, and you actually don't get this to download. And also, like if you have a firmware update, you need to understand these structures. So a lot of these updates are not like a tarball. You can just like unwrap and you know where in memory these things go. So they have like proprietary packaging. All right, so looking at this, so how can we improve the industry so that we can actually move ahead and verify these devices? I think there are 3 pillars, let's say, to this effort, right? And they consist of integrity, transparency, and verification. That means we need to ensure the integrity of the firmware running on the component, meaning that it cannot be overwritten by like a malicious firmware. We need to have the necessary information to actually evaluate as customers the integrity of the firmware and what firmware is running. And last but not least, but to have also the tools, meaning the read primitives and the necessary information to actually check the integrity. Okay, so let's dive into each of these pillars. So integrity. So first of all, I would say there's somewhat like 2 types of firmware. One of them is like the persistent stored firmware in components. That means like this is firmware put into the flash of a component and usually is like field upgradable, meaning you can actually like deploy an update remote. And the other one is like firmware which is actually loaded on initialization of a device. Like a lot of firmware modules actually get their driver through the PCI initialization process. and, for example, grab the driver out of /lib/firmware and push it down into the device. In general, like, think of Joanna's talk yesterday, like, it's the best thing is to actually not have persistent firmware in components, and you actually load them into the device. However, that's probably like not realistic that we get at this point where we all have the persistent firmware out of the component and have it like dynamically loaded. So we need to figure out ways to how actually make sure that the persistent firmware components are better secured. So first of all, when you take a component and you want to make sure that no unintended stuff gets onto the device. So that means that the components should actually validate the firmware they are loading into it. And this can be based on some scheme where you have like a signature on the firmware update that gets verified by the component before actually putting it into flash memory. But as we heard before, like actually having like RSA pub keys hard-coded into like fuses, that's probably not a good idea because the owner is kind of locked out of this device and cannot play around with it. So there are ways how you can avoid this by using a thing called like key duration function-based signatures. However, the signature checks only work for components who actually have sufficient capacity to run like cryptographic operations. And there are a lot of 8051s out there still being used. And running crypto on there is hard. So what can you do to still verify these things? So you can use the OTP approach I mentioned before in the tables of trusted read primitives to build a way how you can actually verify the persistent firmware. So the idea will be that the AP verifies the microcontroller's persistent firmware by actually triggering the OTP ROM bootloader and reading out the firmware bits and then creating a hash which it validates against a base. Then once we have like made sure that only like authentic firmware is loaded into the component, an attacker might still be able to actually downgrade the firmware to an old version which contains a vulnerability. So we need to have like a mechanism to prevent types of rollback. But that's not enough. Like a lot of vendors actually implement debug functionality into their components so they can test them during manufacturing, or if there's a problem, actually figure out what is going on. And these APIs are not documented, but they still might give you a level of access where you actually are able to get right into memory cells and actually get to a point where you get code execution. And if that happens, then your signature check can potentially be bypassed. So we need to make sure that components don't have these backdoors or the test functionality. All right, so apart from this, we also need to make sure that that these integrity checks are also verified. So it means that people who work on this firmware actually should do practice secure development best practices. For example, that they make sure that there is a code review when code gets submitted. And also that there is unit testing and integration testing for like these verification checks, because it doesn't help when these things are implemented and then like another developer comes along, does something, and then break the verification code. Another thing is that component vendors should actually seek out third-party companies to actually do security review on their stuff, so that these integrity protection mechanisms are actually also validated by somebody else. And what also can help is that like bug bounty programs, so that third parties actually help to validate the components. So that's the integrity part of the proposal. The next part is transparency. Like we need to get a better understanding where is firmware actually running in our devices. And we should actually ask our device vendors to give us more insight what is inside the device. So what we could think of is, for example, extend the statement of volatility. So statement of volatility today is something where a vendor of a device actually declares what kind of volatile and non-volatile storage they have in their device. And the idea is, especially government institutions, that when they want to throw out the device, that they know which chips they need to pull to actually throw away the unloved gadget. But we could also like extend this with information about firmware. So let's say it would be good to have at least the minimum like a block schematic of a device where we can see what components are built into the device and how are they interconnected on a high level. Then in addition to that, have a declaration, where is the firmware located and of what type is it? Like, is it persistent firmware? Is it field upgradable? Is it dynamically loaded firmware, etc.? Then the second part of the transparency pillar is that we should, as an industry, get to a point where like the firmware binaries are submitted to like a public binary transparency log. So the idea is to use like think of Bitcoin, you know, like you have a blockchain mechanism where the vendors of firmware send in signed blobs which get included into this blockchain. And that way, like when a vendor starts to do this, the public will actually see what firmware was officially published. So we get some accountability over this published software. And as part of like this blob or like this meta information about the firmware, which gets included in the transparency log, there should also be a copy to the archived firmware. So the idea is like in the binary transparency log, you have information about the hash of the firmware that is published, but also a reference where you can pull a public copy, and this is signed and included in the blockchain. So this makes it like really hard for a modified firmware to go undetected. Like if people actually start to validate against these logs, it should be possible to identify firmware which somebody just modified and put out in use to perform attacks. So this leads us to verification. So we need to get to a point where it's easy for customers to actually perform the verification. So we need to have the components officially support read primitives, and preferably like one of them is hardware-based, where we can get the highest fidelity of read possible. And this is for like very paranoid people and people who do forensics. But we also need the software-based method to like assess a fleet of machines at scale, because if only certain people are targeted in an organization, like it might actually be hard to detect them if you don't have like a broad way of assessing your fleet. And then apart from like the read primitives, we need to have a set of tools and documentation how you actually verify the firmware on a system. So the idea is that you have a tool you can run. It would be able to pull the firmware out of the component, create, like download the reference published firmware, which you can cross-validate with the transparency log, and then actually like compare the hashes of the official firmware update against what you actually measured on the device. All right, so I'm already at the end. So quickly summarizing. So firmware attacks are a super high investment for an attacker, but they last very long because there is a very low chance that it gets detected at this point. Verifying firmware is challenging because there's a lack of documented read primitives and also a lack of a good repository of reference images. And with this, like I propose that the industry has improved in the following areas. that we have better integrity of firmware on components, we establish transparency in public what official firmware is released, and have the particular tools to actually perform a validation of the firmware inside the component against the transparency log. All right, so I'm at the end of my talk. Thank you very much. In particular, thanks to Ron for inviting me to this. I'm very interested to hear your ideas and feedback. So this is my email address and PGP key signature or fingerprint. And now I'm open for Q&A. Yes.
Hi, it's a great talk. Do you see any efforts in the industry that are going in the right direction? Like, do you think the ChipSec is a good direction and we should do more of? Or what are some trends you see out there now that are sort of positive towards some of these ends you worry about?
Yeah, I think ChipSec is a good start. Like ChipSec, I say, has like two main things which I think interesting. First of all, it is an assessment tool. So you're actually able to assess if your BIOS is properly locked down. But it also allows you to pull the BIOS firmware part and actually get a copy of it. So you have like the basis to build actually a system where you can run this at scale. But I think it would be nice if ChipSec had more things to pull from, right? Like it would be nice if we get firmware from other parts of a system through ChipSec modules. But I think there are also things which probably need to be fixed, how the system, or let's say BIOS protection, is designed. So why actually not open up the management engine part to actually have a read possible out of the operating system? That would actually allow us to verify, let's say, against the published MEs out there from Intel.
Right, and the read, you're not looking for public disclosure of source. You just want to see what's the binary object executing at some point for audit, right?
Correct, yeah. Okay. Like we are concerned to get the raw bytes and actually then have a way where we have a cross-reference. So ideally, there would be like a binary transparency log which contained all the versions of the MEs that were ever published.
Okay, and then also, what's your opinion of VirusTotal and how people have been submitting firmware samples? Do you think that's consistent with this direction, or is that sort of a separate class of activity?
I think that's a parallel activity, you know, like the binary transparency log. You could also think of creating a second one where people submit the observed stuff. So like a set of hashes of observed firmware in the wild, because maybe not all the vendors might actually like tie into this system immediately, but people might still want to find out if they are running stuff which other people actually have observed or not. Maybe there needs to be a voting system on top of it. So how many times did you actually see this firmware come by? Things like that. Although I have no like design for how this would work, but I think there's a lot of potential with the binary transparency log. Okay.
And I guess another question, and I'll give the mic back. You mentioned like getting third-party assessment and stuff. Is there, you know, that's a business practice that typically you embark with, you join a vendor. How do you provide proof, though? I mean, part of this is social as much as technical. Do you have any examples of how, when a third-party assessment has been done, the proof, do people publish reports? How do you get some surety that it happened, and as an auditor, and confidence that, or is that possible?
It's a good question. It's somewhat a level of trust which you have with your vendor. So I think probably like the stronger part would be actually to run bug bounty programs. And have like random third parties attest to this, right? And if there are bugs that these get published with a particular disclosure timeline, then I think we probably get a better understanding of how good or bad certain components are.
Okay, makes sense. Thanks.
Yes.
Yeah, so what about, so if you want to validate the stuff if you use your, thank you. So if you want to validate the stuff, if you use it, then you could use trusted boot, for example, implement in each firmware a routine to push or let's say have an instance which does the measurement of all those parts and push it to the TPM, for example. And then you make a trusted boot and you can enforce it at the operating system level. So that would be really optimal. So you don't need to check it again manually.
Yeah, I was thinking maybe there's a way where you could actually like use PCR values as part of the binary transparency log. Then you can use measured boot to get the measurements of the firmware bits and then use remote attestation to basically get a read of these and compare it against the transparency
You
log.
could also use a full disk encryption and use the sealing of the TPM. We already did this. So yeah, it's it depends what you want to do. So if you're a company and you have a proprietary operating system, maybe you want to use a remote attestation. But if you're, for example, a normal user, you could use trusted boot in combination with full disk encryption. Mm. So yeah. It's also it's really nice, but the problem is a lot of firmware doesn't support it. So yeah, that's a problem. So if you could improve this, it would be really great.
Yeah. I also see like potential for validating devices outside of what you just described by utilizing features like closed case debugging, where you extend it to a way where you could actually get access to the raw bits in the persistent storage.
Yeah.
But like when I looked at the Pixel, there's a thing called the servo connector, which is like a connector to attach a server board to do testing on the board. It actually has, like the Chrome OS developer tooling actually has a lot of the bits to actually connect to the SPI flash and the embedded controller bits to do the reads. So there's stuff there, but it means you actually need to open up the device to get to this point. So that's where closed case debugging is a user-friendly approach to that.
Yeah. Okay.
Yes.
So I guess another, what's your opinion on, I know Red Hat recently started this Linux vendor firmware service, and I guess where PC vendors can upload their UEFI update capsules and such, and then use their this firmware update daemon to update. And I guess I think that's an interest.
I think that's
is that kind of what you're thinking about in transparency, or?
Well, I think the capsule update is a way how you securely deliver a BIOS update to a system. Okay. But I think that's only part of the story, because you have a lot of other firmware which has high trust, right? So, but I think it could be interesting if like Red Hat would actually run like a transparency log there, right? Like since they're already receiving this stuff, why not actually send it to a binary transparency log?
Yeah, that's interesting.